All righty, I think we're ready to go ahead and get started. Hello and welcome to today's webinar. We're talking about the overview of statistical process control in food processing. Let data do the driving. I am Christy Grozwinski, Senior Technical Manager at SQFI. Thank you so much for being here today. So the description for the webinar is SPC uses statistical tools to review and reduce production deviations that affect quality and lead to unnecessary waste. Today's activity-based webinar will introduce you to the concepts and benefits of SPC and explain how they can be applied in the food processing environment to lower costs and ensure quality products. Who doesn't want that, right? We'll use food industry examples to illustrate the application of SPC, and you'll learn how to determine process variation and capability and use control charts to manage process deviations that will ensure your products comply with the specifications on a consistent basis. Again, who doesn't want that? Our instructors today are Frank Schurz. He is our SQFI regional representative up in Canada and the northwest of the U.S. And we'll also hear from Bill McBride, who's our regional representative in Australia, Asia. Where's my little button? Here we go. Before I hand it over to Frank and Bill, I wanted to let you know that registration is now open for the 2018 SQF International Conference. Yay! Additionally, the call for session proposals is now open, but it will close on March 19th. So if you got a topic you want to talk about, please submit a proposal. We are always looking for new and interesting speakers. So please feel free. Everyone is welcome to submit a proposal. For more information, visit the SQF Conference website at sqfconference.com. And today we'll be presenting an overview of SPC, which is one of the new requirements found in our new SQF, our standalone SQF Quality Code Edition 8. And for a full overview of the quality systems and the SQF Quality Code, we encourage you to participate in one of our SQF Quality Systems for Manufacturing courses. We have two versions of it, same course, two versions. We have an instructor-led version, which is offered through a good number of our licensed SQF training centers. And we also offer the course, like I said, it's the same content, but a different format in an online format, and this is via Alchemy Academy. So if you visit the Training Centers tab on the SQFI website, you can see the training centers that offer this quality systems course, and you can get access to the Alchemy Academy online course. There's a link there for that. And here's the schedule of upcoming courses from our training partner, NSF. They were a generous contributor to our activities today, so we wanted to be sure to highlight them. But like I said, they're one of quite a few of our training centers that offer the quality systems course, as you see here. So with that, I'll hand it over to Frank to start us out. Let me hand you the controls. You should be good to go.
Okay. You hear me okay, Christy? Is that working?
Yeah. You sound good, loud and clear.
Excellent. Okay. Well, thank you. Thank you very much for that, that introduction, and thanks for all of you for attending the webinar today. And as Christy introduced it, it is called Let Data Do the Driving. So this was this material was primarily, as she indicated, something that SQF and NSF jointly put together, and we did present this at the SQF conference. So put a little bit of a front end to this to talk about some of the code requirements and some of the ways we're looking at evaluating how SPC and or other quality tools are being used in the new code and in conjunction with sites and their quality plan. So we'll start that off from that perspective. So I'll be doing most of the talking today. Bill is on the line and may jump in from time to time. So Bill, I would encourage you to do that if you want to elaborate on anything I'm saying, obviously. So we will then start off. Just going to get that going. Okay, so it's specifically in the code, there's around 6 references to SPC and quality tools that weren't in the previous version of 7.2. So here in a highlight, the first one comes up in 2125, and this is specific to SQF quality practitioners, which a lot of you on the line, I'm sure, are quality practitioners. And the other requirements for the quality practitioner are very similar to the food safety practitioner requirements, other than referencing quality. What's different is this particular element, which basically says that you need to be and shall be competent in SPC, but it also says and or other quality tools, with the obviously implication that you're going to use these types of tools to reduce process variation and reduce changes that may be causing problems with conformance to specifications. So that's the first time it comes up. Auditors will be looking for evidence of that competency, and we'll talk about that in a second as to how they might look at that, just so you have an idea of how you'll show that. The second point where it's mentioned in the quality code is in reference to elements within the quality manual, where it says that it should be and shall include statistical process control methods and other quality tools that are used to control and reduce process variation. So there will be specific requirements or specific procedures and written elements that you would be expected to have within your quality manual as to how you might use these tools. So that's the second part. Continuing on with that, in 2311, it makes specific reference to the use of process capability analysis when you're developing a new product, with the intent there that you would trial that, do your trials, whatever you're doing in the plant to see if you can make that new product on the line, and then use that data to say, well, is your line actually capable of doing that? So there's a specific one for product development, and how you would use some of your data there to show that the line's capable of doing it. The next one under 2543 makes specific reference to using statistical process control methods to control and optimize production processes. Controlled charts, it says, shall be used for control of key processes. It doesn't say all processes, it says key processes, and then obviously the requirement to have upper and lower control limits. And we're going to talk about that, those types of things in this presentation around control limits, where they come from, how you calculate them. We'll give you a little bit of even a chance to try some of the number crunching out. Not too difficult, I hope, but give you a sense of how that's being done and a flavor for that. And a couple other places where it also mentions it's a record of all quality inspections and analysis and statistical analysis shall be maintained, obviously, so they're part of obviously what you're using to improve quality. And then the last piece where we're looking for, and this is in the training component, where it says that line operators, inspectors, and supervisory staff that are inspecting key manufacturing processes shall have training in statistical process control. It doesn't say what type of training, but obviously the tools, the things that they need to use these tools on the line to monitor their processes. The training would be applicable to the level that they need to do the job. So we'll be, coming back to some of these particular code requirements as we go through the course, through the webinar, so you'll have an idea of where they might pop up. But before we do that, I wanted to give a little bit of, we're calling it compliance guidance for auditors, but obviously should also be the type of information that you should be aware of as practitioners or sites that are either looking to get newly certified to the quality code, or are moving from the previous 7.2 level 3 to the new quality code. And And the intent of this is to, again, to provide some guidance. We're going to be publishing this with more clear information, just so you have an idea of how do I move from 7.2 to 8, and what are some of the things that auditors might be looking for, what are some of the things I need to do to ease myself into it or to improve on my previous iteration of 7.2. So in the quality code under 2.1.1, we do talk about obviously establishing objectives. They should be established by senior management, but they also say that they should be measured. And so there should be some correlation and some alignment between the types of quality tools and statistical tools that you use, and obviously that those are measurements, and how they relate back to objectives. So auditors are going to be looking for that type of alignment and where applicable and where it should be. But we're also thinking and seeing and feedback from industry and saying that there might be certain levels of understanding of statistical tools and how they're being used in industry. And so we've kind of provided some guidance and some description relative to being basic, intermediate, or advanced in that area. And I'm going to, in the next slide or two, provide some guidance on that. Certification and evidence of compliance can be at any of those levels, but as it states in the code in a number of different sections in 2.1.1.1, like I said showed earlier, 2.1.2.3, 2.1.2.9, and 2.1.3.1 are all making reference to continuous improvement or improvement in the quality plan, and how that relates to the type of data that you're getting out of your statistical analysis. So the expectation is that as you move and improve on those tools and it shows improvement in the process, that you'll be assessed on that improvement from one year or from one audit to another. If there's failure to show that progression, then the auditor might seem fit to provide a deviation or a non-compliance in that area because of, again, not showing that continuous improvement piece. So keeping that in mind as you're looking at assessing yourself as to where you are relative to being either basic, intermediate, or advanced. So let's take a look just at some of those descriptions before we get going on SPC, just so you can have a sense of that. So under basic compliance, kind of a quality practitioner has basic knowledge of SPC and the quality tools, what they are, why and why they chose to use any of those relative to the types of products and processes that they have. Competency is demonstrated by the applications and how they support the quality plan and some of the quality points and critical quality points that would come out of the quality plan. They're using one or more of the quality tools, Pareto charts, cause and effect diagrams. They're going to show them in the webinar. Run charts with, let's say, maybe even specification limits and how you're using that and how you attempt to maybe move from, say, run charts and spec limits to control charts. And again, we'll talk about that in the webinar as well. Under intermediate compliance, you're building on the basic level that I just talked about, maybe using some more of the tools with the addition of kind of process analysis, such as understanding process variation and the causes that you're getting out of that. Proper applications and choices for sampling and methods of how you sample and collect information and measurements in the process. Sometimes choosing to do it the wrong way in the wrong application cannot provide you with the correct amount of data to analyze your processes effectively. The application use of process control, not with specifications, because we want to let the numbers from the data, as the title said, we want to let the data do the driving. It should be applied at key processes that were identified at your basic level. And now adding different things like CpK, which is process capability analysis, that we'll show you a little bit later in the webinar. and including the recognition of how to calculate standard deviation and the calculations of using the calculations from historical process data. So that would be the expectations at an intermediate level. At the advanced level, obviously you're applying control charts to either your QPs and the measurement of that, or other relevant process points that are important to you. Operators are using and seeing trends in the variation and reacting to them, reacting to what we call special causes. Again, we'll talk about that in the webinar, and basically demonstrating a reduction in or improvement in process variation through the continuous improvement activities. So, we would expect that some of the sites are anywhere, obviously, in the basic, intermediate, or advanced level, and showing some progression from basic to advanced, and in doing so, applying more and more of the quality tools as they deem fit, and showing how they're improving in the processes. So trust that guidance and other guidance that we're going to be sending out will be helpful in for both the sites to understanding where they are, and for auditors to help in their evaluation of that. So in terms of what we're trying to get across in this particular webinar, we want you to become informed about SPC methods and what we mean by that, and how they're being applied in the food industry, and obviously how that application has the potential for identifying cost savings and process improvement. Should also be capable of gathering the data and developing a control chart for any process that's associated with one of your, or any parameter that's associated with one of your processes. I think a lot of the sites that we talk to, and I'm sure a lot of you will agree, that the amount of data and the availability of data is not the issue. There's usually a lot of data. It's just not always being used either correctly or applied correctly, and that can be a problem, because you're maybe wasting a lot of time possibly gathering data that is irrelevant to how you might want to correct or change the process. If you signed up earlier, if you signed up in advance, you should have gotten sent, or should have gotten received a workbook that goes along with some of the things that we're going to be talking about. If you have not received that and you want to get that, if you can put into the chat box your name and your email, and we'll send it to you right away. So if you haven't received your workbook, that's obviously complimentary. Please do that, and some of the people in the office will get that to you during this webinar. So please reach out if you haven't done that. For those of you that do have it, just a couple of instructions. Pages 1 to 10 of the workbook is general information on calculations and templates. We'll be going through some of these calculations. The templates for different uses of different quality tools are there for your reference only. You can use them, or you can manipulate them a little bit if you want, but they're there for those, and we'll be using some of them again later on. Pages 11 to 18 relate to some data that we're going to talk about in the webinar, case studies and examples, so you'll be able to follow through, and I'll make reference to where we are in the workbook as we go through that. And then page 19 is a starting point with some references that you may find valuable to helping you in there, just some reference back to ASQ, the American Society for Quality. There's some really good information there on SPC and some other types of definitions of control charts and things like that. So just there for your reference. Okay, so let's get going. So generally speaking, you know you've had SPC training if you can understand what that whole calculation is, which is basically the calculations for standard deviation. And you recognize it. If you don't recognize it, well, then you probably didn't have SPC training. But it can be somewhat of a onerous to look at that and decipher what that really means. But we do have some stuff in the workbook that actually tries to demystify that a little bit for you. So don't get too concerned about the numbers and number crunching. This is meant to make it simple, but obviously the most important part we want is what do the numbers say and how do we use them. So we're going to be going through that. Earlier I talked about this the practitioner showing competency in SPC and quality tools. So I want to go through some of these quality tools or process improvement tools. Obviously we're going to be talking more specifically around control charting in that application and process capability in this webinar, but there are other process tools that you should look to investigate and see if there is a correct application that you want to apply in your operation. So first one, very easy one, cause effect diagrams are a quick and easy kind of a tool. Some of you may already be using them in root cause analysis, so I encourage you to keep using that. So it might come up as a tool that is handy for you. The other one, a very simple one, check sheets or tally sheets where you're looking at, say, some of the examples here are defects and the correlation defects. So it's a quick and easy type of a tool that basically allows you to then prioritize and correct some of the problems that you might be seeing in that. This can also be used to help you with histograms that we're also going to talk about, and in the use of and there's the histogram there, which is a bell curve. We're going to talk about that and how you use that as in looking at historical data, as well as a communication tool for you in your plants in terms of what the process is really looking at and being able to decipher that from a histogram. So we'll talk about how they're created and why they're important in your evaluation of your data. Then control charts, obviously, we're going to talk about control charts. Here's an example of one. It's one of the tools, one of the primary tools that's used for controlling operating parameters right on the line. Operators can use it, supervisors can use them, and collecting data real time as your process in the process of making your product. Other tools that we also have, the Pareto analysis, scatter diagrams, scatter analysis, or flow charts and run charts. So bottom left-hand corner there, that's an example of a Pareto chart, kind of like what they call the 80-20 rules, where you're trying to show pictorially which problems or which items of concern or emphasis that you want to focus on, so that you basically are focusing on the vital few, as they say, versus the trivial many. So Pareto charts are an interesting tool, and there are some good online, like I say, if you go to ASQ and look at some of the references there, they can walk you through how to create Pareto charts. The second one that we looked at was, just let me get my arrow there, is a scatter diagram. And this is basically where you're looking at the relationship between two variables that you might be measuring in your process. Sometimes it's useful in terms of setting up and measuring something early in the process that maybe, say, controls net weight, and then you can look at that particular parameter versus net weight and correct it earlier so it doesn't become a net weight issue. So they show that correlation. They'll show you whether there is a relationship or not, and if there is a relationship, how you might use that. So it can be a very handy tool to use. And the last one there, basic flow charts. You've already done this, actually, when you put together both your food safety plan and your quality plan. And it is a tool that helps you look at different types of processes and how they interact and relate and helps you with your understanding of that. So those are some of the quality tools that you can use to measure and monitor your processes and hopefully improve them as well. So when we're talking about control charting or any type of measurement, there's two different types of ways that we measure. We have what we call a variable measurement, and these are types of things that we typically attach numbers to, and we measure them: weight, thickness, moisture, protein control, temperature, levels of hoppers, those sorts of things. Very common types of variable measurements that we use in the food industry. And we also can measure certain what we call attributes, and these are more like defects, where we might want to measure or show the number of percent defectives or number of positive swabs we might have even in our environmental monitoring program, number of metal detector rejects, number of packaging seal failures. So these are reject numbers, things that are quantifiable, and you can do control charts with them too. There's 4 different control charts that you do. We don't have time, obviously, in this webinar to teach you how to do attribute control charting, but would encourage you to look for those applications and take some statistical process control chart in more in-depth training that is offered at our a lot of our training centers. Licensed training centers are providing that type of training to do the attribute chart. So the benefits of statistical process control and control charting removes that opinion, removes that feel and guesswork from process control. A lot of times in the food industry, we like to think that it's touchy-feely and it's an artistic type of a thing, and many times it is. But in the end, we if we're making a product, consistency, obviously quality is all about consistency. You want that to be less of an opinion and a feel and more based on an actual measurement that's meaningful, and you can use it to analyze what's going on in the process. And you also want to use those control charts to only make the adjustments necessary when you need to. Sometimes we overanalyze and over-adjust the process when we really don't need to, and control charts are a great tool to do that. The whole idea of control charting is to help reduce or eliminate out-of-specification product, rework, rejects, and downgrades. It's all about, again, that consistent product, using those numbers to help you analyze what's going on in that process. And the one thing I think we underestimate a lot is how we can use the results of the numbers that we collect to communicate both internally and possibly with our customers and our regulators. If you're making an ingredient in the food industry, it's not uncommon to submit a certificate of analysis with your lot of product. That's one form of communication, but it could be very powerful if you could even submit a process capability study to your customer that would show that everything that you're making is 100% within spec. That's the power of that tool that you can now use with your customer in communicating those particular parameters to them. All these tools, and particularly control charting, do assist with the whole continuous improvement aspect and driving out the variation that we commonly see in the food industry. So these are just some examples of control charts. These are from different types of processes. Unless your site is specific to this, it may be different. But determining the capability of a powder filler, actually that's one of the case studies we're going to be using. Analyzing the root cause of packaging. A lot of times packaging and net weight control, that's very common. Most of us are selling product either based on volume or weight. And that's an important tool to use in terms of analyzing, why it might be over or why it might be under, and obviously the implications it has to either giving away product or not being able to sell product that doesn't meet stated weight. A couple other ones: moisture gaining grain products. So all the way through the whole supply chain, we can apply different methodologies and use of control charts to help us measure and monitor what's going on as we make our product. So let's consider this case of a new formula. We're going to use this particular case study through to help us bring forward some of the aspects of control charting and process capability, and so you'll get a sense of how those processes might be changed to get an improvement on the current scenario. So this is a powdered product, like a an infant formula or or powdered milk or something like that, and putting it into a can. So it's new products coming from corporate. That might sound familiar to some of you. Somebody's driving new product development. It varies where that might be coming from. In this case, it's a 15-ounce can, which is equivalent to, this is obviously for U.S. market. They're a long time before the metric system. If you like grams, it's equivalent to about a 425-gram type of can. The powder looks and appears different from the previous product. So it was a new product, but it's looking different, whether it's particle size or how it flows. It was just different. And so we're assuming the site is SQF certified, and to meet the requirements, especially for new product development, we wanted to run a filling trial to determine if we could achieve the net weight that we were proposing to use. In this case, 15 ounces. So they went ahead and did this. It was kind of disastrous. The operators were always constantly adjusting the filler to achieve the target weight. They were saying that the product wasn't normal, didn't flow smoothly, wasn't like they were used to. When headspace in the can increased, they would dial up the filler, and then it would overfill, and then they'd stop and clean up and recycle the product. So there's a lot of stopping and starting and trying to make this product basically fit into a 15-ounce can, and they weren't being very successful at it. So lots of changes going on with that. So what was the problem? Well, a number of things. I think that again, the material could have been different. It was fluffy or sticky. The humidity wasn't going on there. The different things with the filler weren't working. Maybe even the equipment wasn't right. Operators over adjusting. Any one of these, and these might, these are very obviously very specific to this process, but when you're going through this whole thing, and even if you're running your normal product, a lot of times we might not know specifically what's causing changes or problems, so that we're not meeting whatever specification or whatever requirement that we're looking to do when we're making product. Without the use of a control chart, we may not even know if it's a problem. How do we know it's a problem? If we're maybe going by a previous product or a previous solution that may not be the best one to use. So in this case, we're using some fictitious people. Lori, who's fresh from SBC training, she talks to Carl, and he's the supervisor that's working on this particular trial. And she says to Carl, hey, let's do another trial, Carl. But I think let's change something. Let's just set the filler like we normally would for we think it's going to work. Start the line as normal. Just let it run. Let's not make any adjustments. And let's fill about 100 cans, and we're going to take the weight and record the net weight of these cans. So basically what Laura's trying to say is we don't know what the problem is because we're adjusting and changing all the time. So let's just see what the data tells us the line is capable of doing. In 100 cans is not a bad number because it's, in this case it probably wasn't going that fast anyways. Should give us a good sense of what's going on. So fair enough. So Carl says, yeah, okay, let's do that. So they used a check sheet or a challenge sheet. So this is a quality tool that they used, and they basically, on the left-hand side, those are the types of what we call bins, or in this case, the type of grouping that they wanted to do that. So how many times they got, in the case of 11.2 ounces, they've got that 5 times, and then they got 12.4, between 11.2 and 12.4, they got 6 times. So you can see that they were basically looking at what's the distribution of the weights, in this case ounces, that we got over 100 points. So they took that data. That's basically what you're doing in a histogram. And this is basically a histogram on its side, but when we took that data and we actually put it into a histogram, it looks like this. we can drive a lot of, different aspects. What do we know about the process? Where is it centered? There's always a center point. In this case, center was 15.41 average. So on average, most of our cans, of the 100 cans, was 15.41. But the histogram itself shows us that we have some cans that are lower than 15.41, some of them are higher, and it gives us a sense of the distribution of the data. And so I'm going to come back to this histogram in a little bit, and we'll dive a little bit more deeply into it. But let's just look at histograms in general and what they do, and some common types of applications that will give you a sense of what histograms present and why they're important. So this is a mini histogram of conscripts in 1914. So these are, men in this case. I'm sure they're mostly men. There might be some women in there, but I doubt it in 1914. That are being conscripted for war, and they want to see the differences of heights that they were getting. So you can see one lonely fellow over there at 4 feet 10 inches, and you got one or two people at that time that were 6'1", 6'2", but you got a whole bunch that are around 5'7", 5'8". So look at the general population. You would expect that to be the case back in 1914. That most fellows going to war were 5'7", 5'8", and they can use this type of a histogram to predict, what type of, how many uniforms that they need to buy and other sorts of things, and they're probably going to be pretty accurate because that's what the population at this time would indicate. So you can also look at, say, shoe sizes, distribution of shoe size. Versus a male versus female, so you'd expect the male's feet size to be bigger than the female, and this is in millimeters because it comes actually from Europe, but it could actually be in half sizes if we wanted to do that too. And the population on the left side is the female. So what's common to all histograms are you've got frequency on the x-axis, you've got frequency on the y-axis, and basically how you want to chunk out the data on the x-axis. The importance of that is being able to make sure it's a representative of the type of the population of data that you're looking for, and making sure that what we call those bins, or in this case the columns, and where you slot that measurement in, that you have enough of them that you can capture all the data reasonably, but not too few, because then it might not represent the data in the right way. It might not look in the right way. So let's go back to our filler problem. This is again the histogram, and so based on what we just talked about in terms of shoe sizes and heights and stuff like that, I think we can safely say that this particular histogram is fairly normal. It's got this bell curve that we see, that blue line. That's a bell curve. We call it bell curve. It looks like a bell. We can see data and points that are recorded on both sides of the average. You expect that, so equally on each side of that. I'm not going to comment too much on the breadth of the data at this point in time. But when we see data like that, we can basically say, well, the data presents itself in a normal fashion. We can say that that's normal and that the process is stable. If we get any different iteration of that, where it's all flat, it's not showing a peak and equal distribution to either side, we can make proposals that the process is unstable. If you have an unstable process, you can't consistently and accurately apply statistical process control. It doesn't work. There's a lot of other problems that you got to do, so you got to go back in the operation and fix them and get some sort of normalcy to your data. And that's what the histogram allows you to do. By collecting the data and looking at it, you can say, hey, I have a normal distribution, I have a stable process. It gives me some sense of then what can I do to change the process if I want to change the location of that histogram. So it represents your population and represents the type of measurements that you're doing in your process. So what can you do with that? Well, this is where you can start to understand where your process lies in the data relative to your specifications. We all have specifications. They're in our raw materials. They're in our finished products. Sometimes we might get them from our customers. Sometimes they come from corporate. A number of places where that might be the case. So when we now take a histogram and a population and we put spec limits on there, and I like to equate or use the analogy of spec limits to goalposts. They don't move. They're kind of like, you know, the type of thing that you pound in the ground and not going to go anywhere. And so your job, the job of operations, is to take your process and try to aim it between those goalposts and never make out a spec product. Because every time you make out a spec product, I guess you got to do something about it. Either rework it, put it on hold, garbage it, whatever the case might be. That's what the specs are there to do. But the process and the data you get from the process are usually separate from specification limits. We don't know where they always come from. Sometimes they may have used historical data. But the process and the data you get from there will tell you a different story. So in this case, you see that process, and there's a little kind of mini histogram. And it didn't aim very well through those goalposts. So the red bars there basically represent a certain amount of product that's out of spec. Or you can have a situation like this where I kind of aimed in the middle of the goalpost, but now I have out of spec product on both sides of my specification limits. In this case, not a bad job. It's in the center. I'm pretty much at the edges of both of those spec limits. So if my process happens to shift or move a little bit, I'm probably going to make out of spec product at some point in time. This is your best scenario where it's centered in between the goalposts and I have a little bit of what I like to call breathing room on either side of that. So that process can shift a little bit over time, and processes and the data we get from them do shift depending on what's happening in the process. But I've got a little bit of breathing room on that. So the shape of the histogram and where it is relative to the spec limit are important pieces. So we're going to come back to this application of histograms and spec limits when we talk about process capabilities. So let's not. So just put that aside for a minute, and we'll come back to that. So creating histograms are relatively easy nowadays. A lot of times you can have some software packages that do that for you. Personally, I use a bolt-on called QI macro that bolts right onto your Excel software. Very easy to do. But generally speaking, when you do that, it's doing the same sort of steps that's creating here. You got to find your source of data, so you have to find enough historical data that's representative of what's going on in your process. We usually like to say maybe about 60 points, anywhere from 60 to 100 is good, and it might represent maybe a week's worth of process or a couple days, enough of a period of time that you would have seen some common changes, different shifts of people coming in, perhaps different lots of raw material, maybe the temperature in the environment might have changed a little bit, a number of those sorts of things. So you want to take those things into consideration when you're looking at how much data I want to use to create a histogram. And then you got to organize that data into these bins or classes. In our example of shoe sizes, we could have any shoe size from 1 to 3 or 4 to 7, 9 to 11, or we could have used it by half sizes if that's what you're going to do. So you basically set your bins up and the number of bins that you want, and you count the measurements and you put them into each relative bin, and then you plot the x-axis being the bins in order from smallest to largest, and the y-axis has the number of each bin, which is basically what we presented in the previous histogram. So you get a common histogram that looks like this. Again, the value of what you're measuring on the x-axis and the frequency in the y. This is a normal bell curve. Every bell curve, if the data is shown like this, has a mean which is in the center of that bell, and you've got data on equidistant on either side of that. You might get some bell curves that look a little bit different, skewed a little bit to either side, but generally a normally distributed amount of data should look like that. It should look like a bell curve. So when we look at back to our example again, where we've got our data from that second trial that they want to run, where it's 15.41. So if we've got a stated weight, which I said earlier, of 15 ounces, but their average is 15.4, clearly they're making, if they haven't adjusted anything, obviously, they are making and actually filling or underfilling a lot of product. You can see that there's a lot of frequency. They're down at 10.2, 11.4, 12.6. So they're doing that. So they do have some options here to say, well, what can we do with the process? How can we adjust the process? Maybe we want to move it to the right by 4 ounces. So rather than our target being 15.41, we're going to change whatever we have to in the process to make it 20.41. And when they do that, it actually shifts over to the right a little bit more. So we're gonna look at that. But right now, this is what they've got to deal with. So the question comes up then: what do you go back and what are Lori and Carl going to tell management about their progress? What should they tell them? Well, quite clearly it was saying, well, we're not capable of filling with the current formulation, or what we're doing of filling enough jars at 15 ounces. We're going to give a lot of product, not away, but we're not going to be able to fill that can up and make the 15 ounces, and we're going to have to scrap that or rework it. It's going to cost a lot of money. So management's going to go back and say, well, how do we, we've got to get this out to market. So how do we change that? And there are some options that Carl and Lori can do with the process, and we'll come back to it a little bit later and show you, how some shifts and changes to that data can show them, and then they can measure it, and they can measure their capability of meeting their specification when we get to process capability. So back to our histogram and some of the features that we get and statistical things that come into play when we're talking about histograms. So when we look at a histogram, we can say a lot of things statistically around what the data tells us. So when we look at the calculation of all our data, and we put our mean, which is this middle point that we see here. What we can say too, then, when you calculate standard deviation, and I'm going to show you in your workbooks. Actually, I'm looking at that calculation. Just trying to get that page number right. Yeah. So if you look at page 14 on your workbook, what we've done there is taken all the data that we've been displaying in these histograms. And we've shown you, based on the calculation of standard deviation that we talked about earlier, how you actually get that and the particular numbers and how you do that. So I think that would be an important thing for you to learn on how to move from this particular very confusing standard deviation equation, which I showed you at the beginning of the webinar, to actually calculating standard deviation. Because the definition of standard deviation is the average distance of any measurement from that mean. That's why that mean and that anchor is so important. And when you set your standard deviation or calculate it, regardless of what the measurement is, we can statistically say that within one standard deviation, so if you take whatever measurement that is and you add it and then subtract it from that middle point, you can say that for that population data, the 100 points that I took, I can say that 68% of all the points I took are within, one plus or minus one standard deviation. And then you can make similar claims that at plus or minus 2 standard deviations at 95%, and plus or minus 3 standard deviations is 99.7%. And that's why, even in the code where we said plus or minus 3 standard deviations, that's the common statistical reference point to say that if I'm at plus or minus 3 standard deviations, I'm almost got 100% of all my product is within those 2 measurements, whatever that is. Now, these are not specification measurements, but we do sometimes call these control limits on our histogram. And sorry, just trying to advance the slide there. So there's our definition, or our calculation for standard deviation. And that page 14 will walk you through how you actually calculate a standard deviation. And sometimes that's represented by an S for sigma, or this or the sigma symbol. It's more commonly applied using that sigma symbol, and that's what we used in the code as well. So our upper and lower control limit that we would apply to this particular histogram, if we took our middle point and we added 3 times whatever our sigma value was, we'd get our upper control limit. If we took the mean and we subtracted 3 times that standard deviation, we'd get our lower control limit. And once we establish those, that represents what we call the spread of the data in the process. So almost 100% of whatever population or whatever group of data that you would have collected would be within those control limits. And any of the changes that are happening between them are different, what we call common cause elements that are due to the process, and we would expect to see that change between those 2. So now when we go back to our goalposts, and these are in red, as you can see, we take our same histogram that we had before, and now we apply those upper and lower control limits. And you can see that not always, in this case, again, we're seeing out of spec product, and you can see that the red is the difference between the red bar, which is the upper spec limit, and the blue bar, which is the lower control limit, or upper control limit. And that's out of spec product. Here now our goalposts haven't changed; they're there. But in this example, our histogram, or our spread, as you can say, is now larger. Now you can apply those control limits on the outside because we know they're always near the outer points of our histogram. You can clearly see that the process is centered, but again, we're making there is out of spec product being shown on both the lower side and the upper side. And similarly to this point, where essentially the upper and lower control limits are pretty much the same as the lower and upper spec limits, we're doing a fairly decent job. But if that process moves either to the left or to the right, we're going to make out of spec product. The best scenario being in this case where our upper spec limits are outside of our control limits, and basically putting the process in a better place, so we're not making out of spec product. So now by applying control limits, you can see how they relate to the spec limits, and this becomes a very valuable tool in terms of communicating. And in a little bit, we're going to show you how to calculate those values, a value that would equate to and align with this particular process. So let's move into that. So this is called process capability. So in the code, we talk about process capability as a tool for measuring capability of your ability to make specification. And sometimes customers are asking you for evidence of that in their requirements, and if they're not, it's as I indicated earlier, it'd be a really good tool to be able to use. So 2 different ways of measuring process capability. First one we call CP for process capability. In this case, in this picture that we're showing here, we can say that this is where this scenario where we said that the control limits from the data are equal to the specification limits, the goalposts. we can basically say that that's equal to 1. And I'll show you how we do to calculate that. So this is the formula for CP. Basically, the numerator, the top part is basically your upper spec limit minus your lower spec limit, and the denominator, the bottom, is 6 times the sigma values. So if we said the upper and lower control limits were plus or minus 3 sigma, basically that's 3 sigma on the right, 3 sigma on the left. That makes 6 sigma. So when you're looking at the value, the difference between the upper control limit and the lower control limit, that represents 6 sigma. So whatever your standard deviation is, you multiply that by 6. That would be what we commonly call our natural tolerance. Natural being this is naturally what the process tells us we've got. The top part where it says upper spec limit minus lower spec limit, again, that's just the difference between the 2 goalposts. Sometimes that's referred to as the engineering tolerance. So basically, the process capability is a ratio between the engineering tolerance, or what the specification limits are, versus what the process is. And it's a ratio between the 2. If the top, in this case, the top and the bottom are the same, then that's why you get a value of 1. 1 over 1, 2 over 2, whatever it is going to give you 1. So whenever you see a CP of 1, you can say that the process is centered there and that the limits are the same. Not a bad place to be, but again, if the process moves either to the left or the right, you might have a problem. It'll show at a spec, but if you do change that and you haven't changed the control limits, your CP is not necessarily going to change. So CP works well if you again if the process is centered, and you might get some variation change. But if you move that particular process either way, you get out of spec stuff. So on the top left-hand picture there is our scenario, again, where we're out of control here. That would be give you a value of CpkL less than 1. So 1 is equal to the spec limits and control limits. Less than 1, then you're going to get into a situation where you're going to be some out of control product. The same with so in the bottom right-hand corner, what's greater than 1, you have the control limits being and the difference of the 6 sigma being less than the goalpost. That would give you a value of greater than 1. So, so generally speaking, a value of over 1 is good for CP. Now, a better way, and I'm just again pointing it out because sometimes it's commonly used for CP calculations, but CpK is a more accurate way of showing the same process capability. But in this case, you've got to calculate 2 different ways, one on the upper side and one on the lower side. It does compare them relative to the X bar in the process. And it's a very similar, sorry, if it's coming up that it looks like the PowerPoint is not showing up, the squares coming up blank. It should be an X bar in there. My apologies. Sometimes PowerPoint does that when we show it. So the equation is twofold. So you have to do it on the upper side and on the lower side. So the upper one being our upper spec limit minus X bar. So it's kind of the difference between those two, divided by 3 sigma, which is the difference between basically X bar to the upper control limit. And then you also do it on the lower side. Sometimes you might have out of spec on both sides, so you want to do it on both the upper and lower controls. So calculating CpK both upper and lower is fairly easy when you have all the parameters that you want to do that. So I'm going to give you some numbers from our data that we're using back to our fill rate, and I'm going to give you an opportunity to try this out yourself real quick. Hopefully you got your phone with your calculator handy, and some of you can try this. So if the standard deviation, that's our sigma there, of that data that we had collected before, that second run that Lori asked me to do, was 2.38. We already said our mean was 15.4. You saw that in the graph before. Our lower spec limit, in this case, our stated weight is 15 ounces, and they don't like to go higher than 19 ounces. So our spec is basically 15 to 19 ounces. So, so we've got all that information. So we should be able to calculate our CP upper and our CP lower. So why don't you take a minute or two to try to calculate that, and then come back, and if you look at the next thing, I'll go back to the calculations. So you have 4 different answers, and I basically want to know what, and I'll tell you what the answer is in a minute, but I'll give you a couple minutes to do that, and I'll put the CPK calculations up. If you want them, they are also in your workbook, and I'll get you a page reference there. Yeah, on the first page, actually. So, those are control limits. So CPK, yeah, it's on the first page. So they're also on your workbook there if you want to reference them. So give you a minute to try to calculate CPK upper and CPK lower. Okay, let's see what answers you've got. So so your right answer should have been answer C. CPK upper 0.5, CPK lower of 0.56. Both of those numbers are below 1, so not very good. Obviously, we saw from the histogram before that there was a lot of stuff on the lower side that was out of spec, and obviously a very low CPK number does that. But similarly, if they had a spec, in this case of 19 ounces, there was lots of stuff going on there too. So the number that you get should align with the histogram picture. I like to use both of those. So sometimes people like to see numbers, and it's very powerful. You can say to your customer, hey, I just made this lot of product, and I have a CPK of 1.2. That will tell them a lot. That's all they may need to see. But if they also see the histogram, that's pictorially tells the same picture. I think the both can be used as forms of communication, and would encourage that. So basically the guidelines is basically the 1.33 value of CPK is basically saying that we're fairly safe, we've got some wiggle room, we're not making any out of spec product. You get anywhere between 1 and 1.33, well, it's capable, but again, it might shift a little bit. We might be in problem. And if you get a value of less than 1, well, basically saying it's not capable. Your process and the data is telling you you're not capable of meeting specification. So let's go back to our histogram and our value. So Lori and Chad, was it? I think I forget his name. Carl. Lori and Carl had they had some work to do. So basically, what Max said, well, what if we shifted the mean from 15.24 to 21.24, and what would happen? So when they actually did that, and that was about a 21% change, or sorry, a 40% change in the mean, and shifted that, they get a CPK of 1. Then you can do the math. I'm not going to do the math right now, but if you just shift that, don't change obviously the goalposts don't change. All we did was just change the mean. We moved the CPK from whatever it was, 0.0, really low, to 1. But that's a 40% change in the mean. That's what it's going to take so that they basically get to a CPK of 1. The other thing they could have done was a combination. So if they said, well, that's too much of a change in the mean, but what if we change the mean, say, 20%, and we do about a 40% reduction in variation? If they did that, in this case, they actually moved the mean from 15.41 to 18.72, and they change the deviation from, remember before we used the value of 2.38 to 1.36, it gets them close to the CpkL1, not quite, but 0.91. So whatever changes you made in the process, if you're trying to move that, and then you recalculate the control limits, then you can recalculate CpK and say, how have we improved the capability of our process to meet specification? That's the power in that particular value. So you can make the changes, do another bunch of data, 100 data points, recalculate the CpK, recalculate your histogram, and see if those changes are actually allow you to improve on the capability of your product to meet your specifications. So basically, the action plans in this particular powder project, trying to do that was narrowing the spread or the range in the data, so squeezing it. So in this case, we did about a 43% change in the variation, which may or may not be a difficult thing to do. Don't know. It would depend from process to process. So hopefully you can do that. That's the biggest way to drive some change, drive some variation out of your process, and you can kind of squeeze the data. That's going to help you improve on your CPKs as well. But the best tool to do that is a control chart for operators, so that they're not overreacting. So we're going to take a look at some of those control charts and how we do that. So a control chart can be used when the process varies normally. So if we have a histogram and we have data and it's normally distributed, control charts work. If your data is not normally distributed, you can't use that. We have to use some sampling from the process, so we want to make sure that sampling is somewhat reflective of the process, and we want to use that data to detect if there's changes and if there are changes, that I adjust the process. So the control chart, the whole concept of the control charting is different than a histogram. These are little mini histograms of data that we could have collected, and we basically put a histogram on its side, which is kind of what a control chart is, and plot it along our upper and lower control charts. And I'm going to show you some examples of those coming up, but it's basically over time. It's real time and a very valuable tool to do. There are many different types of control charting. We're going to walk you through the most common one, which is an X bar and R chart. It is the most commonly one used. Sometimes people use individuals as well, but let's just use this one. It'll give you a flavor of how to take data and then obviously how to calculate control limits, because that is the important part of a control chart is being able to use and choose the right one to use, and then let that data show you what those control limits are, because that's, like I said, the topic of the webinar was that data do the driving. The data will drive your calculations of your control limits. So we've got to start with something. I don't have any control charts yet. Lori and Carl didn't have them yet, but they have some data. So you need to collect data for a control chart. In an X bar and R chart, we're always looking at a sample size of anywhere from 3 to 10 samples at a set frequency. So you can grab 10 cookies off a line every 15 minutes, or you might be able to grab 3 bottles a minute apart on a bottle filler, because you're going to measure CO2 or something like that. So the X bar and R chart makes use of what we call subgroupings, which are small sets of data that we collect at a certain frequency that should be within that data fairly representative of the type of change that you might see and variation that you might see in a process. So you want to collect maybe 20 to 25 sets of those data. If they're 3 to 4, that may be anywhere from, again, 60 to 100 different individual samples. Could be more, could be less, but that's, again, trying to set up a scenario where it's fairly representative of your process. So as you're collecting the samples, you don't want to adjust the process. You want to be able to get and see the amount of change that you're getting in that process. Then you can use the results of that data to create the control charts or the control limits that you would use on an ongoing basis. And you can create your XBAR and R chart. So if you've got your workbook, and if you can see on page 16, what we did is go back and assume that we're back on our fill line for this powder, and we've collected 21 sets of data, and each set represents five cans that we took off the line. So those 21 points may be 15 minutes apart. So every 15 minutes we would grab 5 cans, and in that in the workbook you can see that for each 5 cans we're measuring what the average for those 5 cans are. We're also measuring what the range of values we have with that, and the range is important because the range within each subgroup is representative of the change or variation in the process at that particular point in time. So the first point in the workbook, you can see that we had an average of 12.8 and a range of 3. The next point we had an average of 16.6 and a range of 3. So it's the average of each of those subgroups that we're actually going to plot, and the average in this case, that's what XBAR represent, average. So we're actually plotting average of subgroups and the range. That's why it's called XBAR and R. So when you get all that data together, historically, you can use it to fill in the required pieces of information that you're going to need to calculate your control limits. You're going to need what the overall average of that is, and that's represented by X double bar. So that's average of your averages. In the workbook, you can see that that's. I'm just going to change the slide here so you can see that. So in the workbook, that's represented as 15.41. The R bar is the average of all the ranges of each of those subgroups. And again, in this example, we have a value of 3.57. There was an error in that page 16. So on the last line where it says average of range and it's an S bar, that should be an R bar. My mistake, I didn't catch that. We do use S bars, but that's for a different type of control charts. For here, we're looking for the average range. So once you know the X double bar for that group of data, and you know the R bar, you have and you know the subgroup size, you can then use all that information and plug it into your equations for calculating control limits. And you'll see that up on the screen now. So you're going to be calculating control limits for both the X bar chart and the range. For the upper control limit for the X bar, it's that X double bar plus this is A2 value plus R bar. So we know what R bar is, we know what X double bar is, but we don't know what A2 is. So A2 we get from this factor table. So you'll see an example of that here on the screen. There's also one in your workbook. And you can determine the A2 value. So you see N is the column on the left. N represents the subgroup size. So in our case here, we had a subgroup of 5. That's why it's highlighted in orange. And then basically you go across, and for the A2 value, you get you can find a value of 0.58. So you can take, so we know X double bar, we know A2 is 0.58, we know the R bar is 3.57. We use all of that information to calculate our upper control limit for our X bar chart. Similarly, for the lower control limit, it's the same minus A2 R bar. We also can use the R bar value for our range for upper and lower control limit for our range chart. And we can get the D3 and D4 values that are represented are there in the equations. We can similarly get them off the factor table. In the case of lower control limit, if your subgroup size is 6 or less, you're always going to get a D3 value of 0. So your lower control limit is always going to be 0 for those types of or sizes of subgroups. And then you can, in this case, for the D4 value, you can use 2.11. So why don't you take a second and try to calculate what the upper control limit for X bar. So we're looking at this X double bar plus A2 R bar. Do a quick calculation and tell me which one of these 4 answers you got. Or you don't tell me, I'll tell you, and then you can just self-check if you want.
Frank, we had a question. I'm not sure if you see it, if you scroll down to the bottom of the Q&A, about changing the mean. It said you would change your processes that you would end up with a different mean, or how do you get a different mean?
Oh,
that was the question.
Okay, let me see. When you're talking about changing the mean a few slides back, did he say that you would change your process so that you would end up with a different mean? Yes. Basically, you have to for any data change, you have to change something in the process. Now, every process is different. So maybe you're changing the density, or maybe you're taking less moisture off, and if you're trying to increase weight. So you would be changing something in the process to derive either an increase or a decrease in your weight. Typically, we're trying to drive weight out so that we can, not give it away, because, overweights are a common cost issue in food. So you wouldn't want to do that. So yes, you have to change something in your process to either, shift the mean or shrink the variation. This, as we're doing here, control charts, I think, are the best tool to continually monitor and use the information. I'll show you a control chart in a minute. It tells you a story about the process, and then if you react quickly, you should be able to drive variation out of that. So, thank you, Christy. Okay, so your quick calculation, you should have got a value of 17.5 for the upper control limit for X bar if you did that correctly. Now, keep in mind, when you do software packages and you choose X bar and R, and you choose your data that you're going to share, the software and the way it's programmed will use these exact calculations. These are universal. The calculations for X bar and R chart. If you choose an individual moving range, which is another type of chart that I don't have time to show you today, they all use the same equation. Same equation. So, but it's good to know, I think, the different elements of those equations and the impact it has. In this case, the range, which is a factor of the variation in your subgroups, and obviously the measure of the variation in your process, is critical to the calculation of the upper and lower control limit for a control chart. And again, we're calculating this differently than we did for our capability, and the reason for that is because these are averages of averages. We don't want necessarily the operator to have really wide control limits that make it very much difficult for him to react to. So let's take a look at that control chart. So here's our X bar chart for that data. You'll notice the upper control limit is 17.5, which is exactly as you may have calculated. We have our middle bar, which is 15.4. That's our X double bar calculation from the data. And our lower control limit, which you didn't calculate, is 13.3. So when we took this historical data and then apply the upper and lower control limit X bar, this is what it looks like. We have on the x-axis the subgroup number, but it's basically a measurement over time. So if you took this and took all the data away and you created a blank control chart for your operators, you'd put those control limits in and ask them as they're recording it to keep within that, or at least have an idea of what's changing. Similarly, we have our R chart, which also comes from that data. And we calculated our upper control limit as being 7.6. Our mean is 3.57. You can't really see it all that clear because it's got some data points over it. And our lower control limit was 0, so we don't even put that on. So this data, and if we assume that they were doing this live or over time, obviously, starts telling us a story. Okay, we have this point. I think it's our fourth or fifth point. It's at 10.8, way below the lower control limit. Something's gone wrong. We see some variation. So we would expect the operator to react to that and adjust it and bring it back up to within the control limits. So it's reacting to what we call a special cause. Something's happened, and he knows that because it's the control limit from the data is what they should normally be working within. Similarly, here on the range chart, if we remember this point here, I'm pointing to on the R chart coincides directly with the range value. So you're always plotting the X bar in the R at the same time. that's clearly above the upper control limit for the range chart. So similarly, we would expect the operator to react to this. They're not reacting to necessarily a problem with the X bar value, but they would react because there's a problem with the R value. The other thing that control charts are great is they start showing us what are some trends. In this case, we've got a bunch of points all above the mean of 15.4. We should see that. If we're seeing common cause variation, we would expect to see an equal number of points above the line, the mean, and below the mean. In this case, over a period of time, it's trending above the mean. So that would tell the operator that, hey, we're probably running a bit high. We're not out of control yet, but if we stay there, chances are we're probably going to be out of control at some point in time. So let's bring that process back down and change something in the process and do that. So trending like this is very helpful as well. And I'm going to show you a couple other trend tools in a minute to get to. So you got the data you've seen, and on page 17 you've got that same in your workbooks on page 17. That's the same control charts that I just showed you. But this is a very common way of doing control charts on the line, either pen to paper or electronically, where you have the X bar and R chart on the same page and the data right below it. So they're recording the data and they're recording the ranges and the average. Sometimes they have spreadsheets that do that, or sometimes they have little calculators. And then you can plot the X bar and R and then they can react to do that. So if it's done real time and the operators see the out of control situation, then they can react to it. Now these control limits, it's recommended that you set a frequency of looking at data and seeing, do I need to recalculate the control limits? You can set that on a monthly basis, every 2 weeks. You set the frequency, I think, based on how much change you might expect or how long you think it might be for operators to use control charts and drive variation out of the process. It may be a very long time, but at some point in time, if they're using the control charts properly, they will be driving out. You will see improvement, and when you recalculate those control limits, they will get smaller because your range values are going down, and that's a good thing. At some point, you won't get any more improvement in those settings of the control limits, and that's usually the place where you've looked at all the different things that affect variation in your process, and that's as good as you're going to get without maybe buying new equipment or something else. And that's a good thing. But at least you know, and you've got a tool now, so that if something does change, and in the food industry with variation in materials and a whole bunch of other things, it's not uncommon to have special causes happening. But then you're going to react to it. So in these cases, you're reacting to the process. Nowhere on these control charts do you see specification limits. They should be a lot wider than them, and you want to be acting to the process, not necessarily to the product. And I think sometimes when we put specification limits on control charts, along with control limits, they can confuse the operator in terms of, when should I react and when shouldn't I. But if the control limits are there and that those control limits come from their data, they should trust that. It becomes a very valuable tool to use. So common cause and special cause variation, mentioned that earlier. You see that all on those control charts, all that oscillating above and below the mean are common causes. The special cause, we saw that example of that. Here's also what you can do is in a control chart, we can sometimes take the area above the mean and the area below the line, and we can segment that into 3 zones. They kind of represent sigma in some ways because they're equidistant zones. But when you do that, then you can apply different control rules or trending rules that tell you, say, if in this case you saw that clearly that 1 point on point 10 is a special cause, it's way above there. But you can also say that, hey, if I've got 2 to 3 points in zone B, I should maybe alert myself to say, hey, that's not normal. Or if I've got trends going in a couple of different ways. So if you look at this chart, we have trends going up or trends going down, maybe 5 or 6 in a row. Some trending rules say 5, some say 7. You should probably pick the one that probably is over a frequency of time great enough to indicate to yourself that there is a trend. So you can see that in the first 2 circles there. And in this case here, where the square box is, you start to see a number of points in that second zone. So we have one zone from the green line to the first dotted line, and then in zone 2. So sometimes the trend rule will say, hey, 4 to 5 points in zone 2 or zone B or greater. You can use numbers or letters. It doesn't really matter. Should alert you to the fact that, hey, you shouldn't have that many points out there in that zone. Most of them, again, we said 68% of our points should be within the first zone from that mean. So that tells, again, the operator that something's going a little funny in the process and that you want to be alerted to that. So keeping an eye out for that. So I think the takeaway from the use of SPC charts is they are indicators of change in the process. It's a tool to measure that change. It tells you where the special causes are. We can look at different runs or points above or below the line and trends, and sometimes a reaction to what we're going to do with that. So it's kind of an overview of what we talked about. I know it's really quick. In an hour and a half, it goes very, very quickly. We want to determine that the process is stable and follows a recognized pattern. So that's where we collect data. We create histograms. We do process capability on that to see where that data is relative to our specification limits. And then we use SPC control charts. I showed you an example of X bar and R. Like I said, the individual moving range chart can be used. We talked earlier about attribute charts, and attributes can be things like rejects. They can also be control charts if they're important quality parameters. But in either case, you got to collect data. You got to collect some, do the math on it in terms of calculating your control limits. Put those control limits on our graph. Start plotting them. Start using that data to react to out of control conditions or trends. And every time you're doing that, you should be driving variation out of the process. That should drive down costs. That should improve your quality, and you should be able to see that in terms of your compliance to specification. So that pretty much takes us to the end. And we do have a couple minutes for Q&A. Christy, is there anything, any other questions that came up? You want to try doing some of those? Or?
Yeah, maybe one or two. Keep in mind that some of these questions that you have are covered in the SQF Quality Systems course. And as I mentioned at the top of the webinar, the course is available through our training centers and online through Alchemy Academy. So if you visit the Training Centers tab on our website, you can see how you can access either an instructor-led course or an online course. And one of the questions that we have, again, if you scroll down to the bottom of the Q&A box, it says how the values of the factor table for the upper control limit and lower control limit are calculated. So if your methodology varies, how do you know which factor to use? There's one of our questions.
Well, the factor table is driven by your subgroup size. So if you set your subgroup size, let's say 3, you would always use that same factor table. If you change your methodology, meaning you change how you sample in your subgroup size, then you're going to have to take that into consideration and use a different factor when you're calculating control limits. I wouldn't necessarily change subgroup size and factors because you're trying to get a control limit that you can live with. You got to pick the sampling and the frequency and the subgroup size that works for you relative to what you're measuring and how you're doing it, and it should be reflective of the change to do that. I wouldn't try to manipulate that. The data usually tells a pretty accurate story if you're sampling properly and doing that methodology. But remember, sampling and methodology and how you do it and how you measurement, there's error in that too, and that can be part of the the picture of variation. So you want to be able to do that correctly. And that may be some trial and error that you got to figure out in terms of which method is best at representing the type of variation that we want to gather in that process.
You know what, I think, unfortunately, we'll have to end it here. I don't want to go too much longer, but Frank, if you go to the next slide, you'll see that our contact information is there. There you go. And if you have any additional questions for Frank, you can send it to Frank and then Bill McBride as well, or you can send it to any of us, quite frankly, or our info@sqfi.com email, and we'll direct it to the right person. So if you do have a question, you can send it to any of these lovely people here. And I do want to mention that we have recorded this webinar, and we'll send you a link to the recording along with a copy of the slides within a few days. Give us some time to clean up the presentation recording and make sure that it's nice and smooth, and we can email that out to you. It's also going to be available on our YouTube channel. And with that, I'd like to thank Frank so much for this wonderful information. That was really some great information. I know that I learned quite a bit as well. And with that, I will thank all. Thank you all so much for your time and your participation, and we'll wish you a good evening or a good day.